Okay, so welcome everyone, and it's a pleasure to have with us the second mini course for this summer by Kavita Ramanan from Brown. And just before we start, a quick announcement that there will also be another series of mini courses taking place this July and August, and we will be sending out some general announcements later this week. But keep your eyes open. So please, Kavita, and you can get started with your first lectures.
Okay, thank you very much. It's a real pleasure to give this course. Sorry it's not in person, but let's try to make it as interactive as possible. So I'm going to be which means please interrupt me whenever anything is unclear and just ask me. Okay, so I'm going to be talking about asymptotics of interacting stochastic processes on sparse graphs. So first I'll start with a prelude to the course where I describe the main problem I want to look to, give you some background and motivation, then the outline of the course. And then I will start today's lecture. I will use slides a little bit today, and then I will move to sort of the more interactive style of the iPad later. Okay. So what's the basic problem description? Suppose we are given a finite connected graph. And I should also mention I will be posting some background material later today. I was just trying to get a sense of the audience before I do that. So, okay, you give a finite connected graph and then use, this little tilde to use the usual neighboring relation. I will use NVG to denote the neighborhood of V. And dV will denote the degree of V, which is simply the cardinality of the neighborhood. And we're going to look at stochastic processes where each node has a particle whose stochastic evolution depends only on its own state and symmetrically on its neighbor states with respect to some underlying interaction graph G. So you might have just n particles, and then their dynamics is determined by this underlying graph structure where the infinitesimal evolution or the instantaneous evolution in the discrete time Markov chain case depends only on the states of the neighbors and itself. And so one could consider, of course, different kinds of dynamics that does this. And in fact, our work does do that. But today, I will focus on two cases. The first is the discrete time Markov processes. And the second will be diffusions. Okay, and such models describe a range of phenomena in statistical physics, epidemiology, neuroscience, math, finance, etc. So let's give a more concrete model. Okay, so I fix a finite graph. You have some initial condition on the configuration space. My chi is going to be the state space. And then my discrete time Markov chain, which is this structure is often called a probabilistic cellular automata or synchronous Markov chains. So at each vertex, so I'm considering only Markov processes right now. So of course, xg at time t, which is this whole configuration, could depend at the whole configuration at time t. But in this case, it'll only for each vertex, its value at time t plus 1 will only depend on its own state at time t and its neighboring states at time t, and then some external random noise. Okay, so this is the structure of the local. So whenever there's some locality, I sort of highlight it with a blue color. And so you have some state space, which is Polish, some noise space, which is Polish. You can, that's really, you can often take it just to be uniform 0, 1. And you have some continuous transition function, which goes from chi times, I'll tell you what this is, just sort of, this is representing the neighborhood states, and then the noise back to the state. Okay, so it maps your state, all the neighborhood states, and the noise back to the state space. Now, this is just a general way of writing. I want to say that the dependence on my locality for this talk is going to be symmetric. So there are different ways of representing that symmetry. But we will choose to represent the symmetry, just saying that if I'm giving some sequence over there, which will depend on the degree of that vertex, right? That's why this notation looks more complicated. If it was a regular graph of degree k, this would just simply be chi to the k, right? And then sort of modded out by the permutations, because it's permutation invariant, right? So, and so this is just a way to say that I only care about what is the collection of states and not the order in which they are. And so this is, don't worry about too much about the notation. You might say, why are you complicating it so much? Why not just use the empirical measure if it is symmetric, right? So one could just instead look at the empirical measure of the states if I'm only interested in symmetric quantities. But you see, then you would naturally endow this empirical measure state space with sort of the weak topology on probability space, and continuity with respect to that is not so nice sometimes. So for instance, if you want to look at the maximum value, it will depend on the support of this distribution, and that's not always a nice continuous function. So you don't have to worry about these details, but this is just to tell you why we're using this symmetric. But you might, a lot of the examples I'm going to do are going to be, in fact, you can think of the dependence here as just through the empirical measure of these states. Okay, any questions? Okay, and okay, and then these are called probabilistic cellular automata or synchronous Markov chains. And of course, there are many examples of these. These are generic. So for instance, you can have the discrete time contact process where the state space chi is just 0, 1. In many cases, you have finite state spaces which represent healthy or infected. And you have some two parameters, PQ, and the transition rule at a time t, the evolution state of a particle at any node V depends on the state of that particle and the neighbor's empirical distribution, as I said. So this is defining explicitly where this is the Dirac delta function at the state. Okay, so what is it? So in the sense, the precise way in which it depends is if state xvt is equal to 1, it switches to xvt plus 1 with to be from 1 to 0, which means infected to healthy, so it recovers with a probability that's independent of any of its neighbors, right? So it's just the recovery rate. But if it is healthy, then it will get infected. It's a rate that is, or a probability that is proportional to the number of the neighbors that are infected, or the fraction of the neighbors that are infected, not the number, okay? So the fraction, and you can therefore represent this in terms of this. Okay, and here I've not put in the noise processes explicitly because these are just Bernoulli to tell you with probability PQ, and you don't really need to write that in that form. Okay, any questions? Okay.
Yeah, so just a quick question. So,
yes, please.
So you assume the function you assume is the same for every vertex. It doesn't depend on.
Yes. So for not all our results, we don't need that, but for simplicity, I'm assuming right now that f is the same function everywhere.
And
for some of the results, I'll clarify it can be heterogeneous. Some of the other results, it needs to be homogeneous.
Okay, and then when you say it only depends on the empirical distribution, so if you have a vertex with one neighbor that's a 0 and one that's a 1, or another vertex that has 2 zeros and 2 1s, then they should evolve in the same way?
Yes.
Since you have this, so it only depends. Okay.
Yeah, it only depends on the fraction.
Okay.
But that's in this contact process model. But that's why I allowed. In fact, that's a very good question, because that's why I allowed the more general formulation, where you could depend on the number. So if you go back here, I allowed it to depend on this sequences. And so there, I could also allow it to depend on the number of zeros and ones. And that's actually one reason to do this generality. Whereas, because that could also be symmetric, right? But you just care about the number of zeros and one. This allows you, so our more general framework will allow it. This is just a particular example in which now I don't care about the numbers. Yeah, okay. So, okay, and then there's of course many versions of this. For instance, you have versions of sort of epidemiological spread models. Another one is just called the susceptible infected recovered process, which has 3 states, S, I, and R. And if it's in the susceptible state, then it goes to the infected state with some factor P times the proportion of infected neighbors. And then once it's infected, it will not become, it will just recover. Once it recovers with some probability Q, again, that's independent. So that's the same as in the contact. The difference is that once it's recovered, it does not become susceptible, right? So in the contact process, as soon as it's recovered, it's susceptible again, but here it's sort of a monotonic progression. Okay, so that's another process that's well studied and and then there's so sometimes the contact process is called as SIS. And there are many different versions of these models, which I'm not going to get into right now. Just an example. These are just illustrative examples. Or we could also consider networks of interacting diffusions. So now again, you have this finite graph, some initial condition, and then now again, it evolves as a diffusion where the drift coefficients depend on the current state. So I should put T here and T here, and then depends on the neighboring states. And then they're driven by both the different diffusion coefficients. And I assume that they're both Lipschitz continuous so that this SDE has a nice solution. Okay. And we have IID Brownian motions that are coming in. So note that each XVGX again takes values in the space of continuous functions, taking values in RD. These are all D-dimensional independent Brownian motions driving this process. And I will denote that by CD. Okay. And again, we are using the symmetric thing, but often it may depend on the empirical measure, but we allow both. Okay, and I haven't really told you exactly what the topology here is, but it will be more general that will allow us sort of a more general functions. Now, I am just restricting this discussion today to Markovian systems, just because I want to get across the main points. But in fact, many of the results, the results that we consider hold for more general functions where you're not just depending on the state, but you're depending on the history of your own state and maybe the history of the neighboring states. Okay, so it could be more generally progressive measurable coefficients. That's if in case anybody's interested in some model like that. This is both in the Markov chain case as well as this case. Okay. Okay, so now you have networks of interacting diffusions, and one example that arises, these sort of models arise in neuroscience, but also in systemic risk in math finance. For instance, here you consider sort of independent Brownian motions, of course, driving this process, and each XV here represents the risk of a particular agent or a company. And that risk evolves according to some restoring potential, which is some function U and some H is some value. And then it has some theta, which is a sort of the mean reverting, but mean reverting only to the local mean. Okay, so it's local empirical mean here. And then you have some noise. Okay. And so you're often interested in, is the risk that in an interconnected system, if each of them is likely to fail, which might be XV going below some value or going below the mean, then what's the probability when they're all connected like this, that these different H's and theta strengths tell you something about, H tells you about the individual likelihood to fail in the system, and then theta tells you the level of interaction, and people are interested in sort of for different values of H and theta, when and what kind of connectivity patterns will you have sort of the whole system failing, even when maybe individuals are not failing as much. So these sort of dynamics are of interest in systemic risk problems. And this has mainly been studied in the case when the graph is the complete graph, not so much the topological setting. Okay.
So can I ask a question?
Yes, of course.
And when you say neighborhood, you mean only the first neighbor, right?
Yes, this is just remember the neighboring relationship.
Okay, it's only the first one. It's not that.
Yes, I mean, if you wanted to remember on two neighbors, you simply just redefine your graph.
Yeah. Okay.
Yeah. So you put your graph as all the ones that you depend on.
Yeah, I'm just wondering about the systemic risk application that one can.
Yes, so you just change your graph structure. So then it will always be just the immediate neighbors.
Okay, thank you very much.
Okay. Okay. Yeah, so for instance, if you have some graph in mind and then you decide you suddenly want to look at what happens when you connect two neighbors, you simply look at the square graph, which connects everything that's within distance 2, and then just look at the dynamics on that graph. So, okay. Okay.
Yeah, sorry, it's
Yes.
related, but the level of a neighborhood has to be the same, in the sense I take into account two level, but I have to take into account only the two level connections.
So
no, it cannot be that one point has is more connected in some sense. No,
I understand. Like, can you be heterogeneous in the way you
yeah, exactly.
neighbors? And it actually turns out that so I'm looking at the simplest version here, and there's another compelling problem that comes for jump Markov processes, that we have extended the theory to deal with those things as well. But for today, I'm just going to talk about the most simplest case. But we can deal with sort of the heterogeneity in your neighborhood, because it's still symmetric, saying sort of your immediate neighbors, you interact in one way and you interact with the sort of two neighbors away in another way.
Yeah, exactly.
Yeah,
exactly.
You can do that, but I don't want to. I want to just sort of exposit the things in the basic model now, but I'll be happy to talk more about the other one offline. Yeah.
Thank you.
Okay. So, what kind of quantities might you be interested in these models? So one quantity of interest, of course, includes the global empirical measure. You might want to know what is the fraction of, different values, fraction of particles taking different values. So, and you can look at, the global empirical measure on path space, which I'll denote by G and X. By the way, all the superscripts always relate to the graph and the initial conditions, okay? And then here I have, when I have a T, it is looking at the, empirical measure of the particular states, which I rewrote here, okay? So this is an element of, probability measure. It's a random probability measure on path space. And this is a random probability measure just on the state space, okay? Okay, you're interested in both these quantities, for example. And so we have these, possibly a Markov chain, we might have a diffusion, and we have these global empirical measure process. And what are the key questions? So given a sequence of graphs, with the vertex size going to infinity, because what are we interested in? Understanding the behavior of really large systems. And we want to understand, do these processes, and xn's also, sort of, you have to mark them with initial conditions. Do these processes converge in some suitable sense? Okay, that's one thing you want to ask. Another thing that you might want to ask is, do the global empirical measures converge? Right? And then, and this is sort of the main thing that I'm really interested in. Also, I'm in all three, but then maybe this is a sort of really not obvious one at all. Can one somehow autonomously characterize the limiting dynamics of a typical particle? So if assuming the limit exists, assuming one is true, it does converge, then, what is it? What is that dynamics, right? If it does converge, can I somehow describe that dynamics? Okay, so those are the questions that we want to address.
Excuse me, can I ask a question, please?
Yes, please.
Yeah, so can we answer the first question without identifying the limit? Because to me, in general, we have to identify the limit to make sure that that we have convergence by using those differences between the distances. But maybe there is a case where we know that it does converge, but we don't know exactly the limit. Is it possible to have this case?
So are you saying sort of you would require 3 for 1? Is that what you're trying to say?
Yeah.
Yeah, so there are two answers to that. One, of course, you could have this existential result. You could see that it's Cauchy, and then you know that there's a limit, in a suitable, if you have, sort of embedded in a nice metric space, you can say it's Cauchy, so it has a limit, but I don't know what that limit is. But it'll become clearer in a minute.
Okay.
As to why you can do 1 without understanding 3. The key to 3 is, I am saying, can one autonomously characterize the limiting dynamics? That means I want to just define XV, its dynamics, without reference to any of the other particles.
Yes.
Okay, so that's a little different from just understanding the limit of this. And it'll become clearer, but it's an excellent question. So thanks.
All right, thank you so much.
Okay, yeah. Okay. So like I said, that's the problem formulation. And so what are the background and motivation, like, classical results that we know. So for simplicity, just so that we don't have sort of too much notation going around, I'm going to look at the particular case where you just depend on the empirical measure. And also I just get rid of the diffusion coefficient. I mean, in the sense that I just make it the identity. Of course, I don't get rid of it, I need it. So it's non-degenerate, just an identity. Okay, the results don't require all of this, but just, to keep it simple. And so now I'm looking at the small b, which was a function of xv in the neighborhood in some symmetric way, is now replaced by this cap b, which is now a function of, in this case, rd, and probability measures on rd, which are these local empirical measures. Okay? And so, of course, in the particular case, when you take b is linear in the measure variable, so it has this form, then it just takes this nice sort of averaging population. You can think of b bar here as a sort of interaction potential amongst neighboring vertices, right? But the point is that you can look at more general functions, but this is, if you can look at b's which are nonlinear, but this is a sort of generic example that you might also look, where here you're just taking sort of the average influence of your neighbors. Okay, in this particular case, sometimes things simplify a little bit because b is linear, but we don't necessarily require it. Okay. So like I said, the well-studied case is when Gn is equal to Kn, which is the complete graph. Okay, so everyone's connected to everybody. In this case, by slightly modifying b, because strictly speaking, the b would depend only on the empirical measure of the neighbors, which would remove itself, but I can slightly modify b to pretend that this is the global empirical measure, right? So I'm just going to call it b again, but I can, if it's a function of the current state and the empirical measure of everything else, I can always write it as a function of the current state and the global empirical measure. Okay, so now you have this form where I'm writing b. So, b is again a function from rd, prd to rd. And I'm making the diffusion coefficient the identity. So let's try to see some intuition. Of course, many of you may know sort of what the limits here are, but just to keep everybody on the same page, let's try to get some intuition about the limits, about what limits might exist here. So if b is equal to 0, of course, we're in a very happy state. If we assume all the initial conditions are IID, then if you look at this global empirical measure, each of this is just a Brownian motion starting at some random IID initial condition. So you have independent Brownian motions. So obviously mu n, the one which is on path space, will just converge weakly to some deterministic measure by strong law of large numbers, which is the expected value of the Dirac delta mass, which is simply Wiener measure starting at an initial condition, which is lambda. Is this clear? Right? So I'm just looking at this and saying, okay, this is a strong law, so it's called the expectation, and the expectation is simply the law of any one of these, which doesn't change with n. So it's really, really simple. But the question is, what if more generally that's not true? We don't have b equals 0, but we still have mu n converging to some deterministic measure valued process mu. Then, since b is continuous with respect to the measure variable, one might expect, okay, then that x might converge. You could replace mu n here by mu, and then you say, okay, x must satisfy this equation. Does that make sense as a sort of conjecture? Okay. So, but however, this doesn't autonomously characterize x yet, because you don't know what mu is, right? Yet. But of course, we think we should also have a guess for what mu is. I'm just saying, by the way, rho is usually going to be some generic vertex for me. Okay, so that's why I'm writing this rho here. So mu of t, remember in the past one, it was just the law of x of t, right? In the first one, when b is equal to 0, it's actually the law of xn of t for every n, because it's not changing with n. But here you would expect again mu, again by the sort of strong law for some correlated Where is that? Again, you would, sort of go to the limiting expectation, and that may be the law. So this is something that you may guess is true. Okay, at least this is the intuition, that mu of t is again the law of this process. Because mu t, remember, is just this 1 over n summation v equals 1 to delta x v, and then if you take the expectation, then you do expect it to be the same. If it concentrates, then you do expect it. Since it's deterministic, you might expect this concentration to hold. Okay. Okay, so in fact, this is a very, very classical result that goes back to, McKean's 1967, and then Olschlager, Schnittmann. There are many, many treatises that talk about mean field limits, and the people know this in much, much far more generality and, in control settings, etc. But okay, so if you have sort of initial conditions, this should be 0. So initial conditions are IID with common law lambda, and B is, like I said, Lipschitz continuous in both variables. And then mu nt converges in probability to the unique solution of this McKean-Vlasov equation. Okay. And of course, the reason is in the first case, we actually, in this B equals 0 case, we actually had the particles independent. But the reason it looks similar in this case is because asymptotically, these particles are becoming independent, the sense of at least any finite number of particles are becoming independent. Okay. And why is that? Because you can sort of get that because, each particle is being affected. So any vertex particle at vertex P is affected symmetrically by all its neighbors. So sort of the strength of interaction from any one particle is like 1 over n. And so as n goes to infinity, you think that this is decay. And that's the intuition. And more generally, I assumed IID here to make things simple, the initial conditions. But in fact, it holds more generally when the initial empirical measure converges to some deterministic lambda. And then you also have, then at any time t, you have this convergence to this empirical measure mu t. So that's called propagation of chaos, chaos being referring to the fact that the empirical measures are converging to something deterministic. And you're saying if it happens at 0, it happens at every time t. And in fact, it happens for all sample paths, okay? And so that's the intuition. Yes. Now, note that X is a Markov process. And so, right, it's a Markov process because this is just some deterministic T. So we can think of this as B as a function of T and XT, right? So it's just a diffusion, the drift that depends, but it's an inhomogeneous Markov process because it's, this drift is could be changing with T, but it's not just an arbitrary inhomogeneous Markov process because the dependence on T is only coming through the law of the process. And so you can write down the forward Kolmogorov equation for this process. And you will see that, well, if there was no mu dependence, this would be linear PDE, right? But in this case, because you have this mu dependence, then it becomes a nonlinear process. And that's why these things are called nonlinear processes. Okay, so I apologize to those who know mean field limits really well, but I'm just sort of reviewing it for everybody. Okay, so this is well known and, like I said, known in much greater generality, but this may be addressing a little bit of Zoe's question. So if you can also take a slightly different perspective, I'm going to tell you something about the proof of this, but I will actually be giving you a short proof of it tomorrow. Because we will need it for something. So, but here, if I look at a slightly different perspective, in the case of a complete graph, you can actually deduce the existence of a limit from very general results. Remember, all these xins are all exchangeable. Now, for this, Omer, I am assuming that it's the same f or the same b for every v, right? So, okay, now you have complete exchangeability. And so if you have exchangeability, you can, from very general results, say that you will have this limit, and this limit xin converges to some xi infinity, and this limit exists. Where xi, x infinity is this infinite system of SDEs satisfying this driven by this mu t. Okay. So this can be done, and this is a view that Kurtz and Kotlanes took in a paper where they were actually looking at much more general processes, including SPDEs, and saying that, well, once you have exchangeability, you can actually have this kind of limit result very generally. So In other words, I can say here that xin goes to xi infinity, but look here, I have said mu t exists, but I haven't related it to the, x1, or I haven't said exactly what SDE it satisfies, right? And so in some sense, you can think of the McKean-Blasov limit as describing the local or marginal dynamics of this infinite particle system, right? It's saying any one of them, its law evolves according to this, the McKean-Blasov. Yes? Okay. Anyway, it's good to have both of these perspectives. But now going back to the propagation of chaos perspective, we might say, okay, we might not always have complete graphs, right? You might not always have interactions that are, fully interacting. And maybe you just, are connected to some subset of your neighbors, or influenced in a local way by a subset of your neighbors. Then what happens? Now, as long as these graphs are still dense, in the sense that the degrees in the graph GN are converging to infinity in a suitable sense. So you have to ask, is it the minimum degree? Is it the average degree? Is it, so you have to put specific conditions, but I'm not going to go into those details for us now. But you can see that I'm just looking at this particular kind of equation, right? You can see here that you have, like I said, any one particle is affected by its neighboring particle, inversely proportional to the degree of that vertex. And so if the degree is going to infinity as n goes to infinity, you might expect, okay, once again, you will have asymptotic independence, you will have propagation of chaos. Once again, the global empirical measure, there's enough sort of this decay and mixing that the global empirical measure will converge to a deterministic limit. And once it's converging to a deterministic limit, then of course you can then plug that back in, and the typical dynamics will again converge to the same McKean-Blasov limit. So you actually do not see the structure of the topology of this graph that was dense. You lose it in the limit. I mean, if you're just looking for a single particle and how it behaves, right? And there were many recent results over the last 4 or 5 years that made this precise for different graphs. Now, of course, here I'm always sort of talking as if the graphs were deterministic, but you could also, have the graphs random. So the graphs themselves could be Erdős-Rényi, and then, you define this for each realization of the graph, and you get a random process, right? And then you can ask what happens to that graph, and we will be looking at things like that. So Delattre, Giacomin, and Dusson, for instance, they looked at the case when you have an Erdős-Rényi graph, G and Pn. So remember, that's n vertices and independently choose with probability Pn edges. And if nPn is converging to some value C, then, to infinity, sorry, nPn is going to infinity, so that the average degree of that graph is going to infinity. So that's capturing this dense condition, and with some other minor conditions. Then they show that in the Erdős-Rényi graph, you will still get, so the individual particle will still go to what is the mean field limit. And similarly, there were various different versions for deterministic graphs and certain other conditions. So here's just some sampling of some of those papers, and I will put up references and everything in my notes at the end of the day. Okay. So,
Kavita,
yes, please.
Do you know if there is this kind of result for d-regular graphs?
I'm going to talk about it.
Okay. Okay.
So thank you for bringing that up. So Delattre, Giacomin, and Dusson actually brought up the question of what happens if, for instance, example, nPn goes to some value C. So it's sparse, right? So I'm coming to that. Thank you for...
But I mean for d-regular graphs with d going to infinity.
I think, okay, with d going to infinity, so dn going to infinity. I think there might be some results. I'll have to look, but I'm not completely sure. But I think there might be some results.
Okay, thank you.
Because some of those deterministic papers, so there are some of these papers looked at sort of deterministic graph sequences, which is not, of course, a d-regular graph. But then they had very general sort of conditions on the degrees, which might be, verified for sort of instances of d-regular graphs. So I will look it up and I can send you details.
Okay, thank you.
Okay. So now you can ask, these mean field, what is the brilliance of the mean field approximation is really the fact that if you saw that, you have this complex system of highly interacting particles, but then in the end, if you want to understand the behavior of just one particle for large enough n, you only have to look at an RD, so if D was 1, just a one-dimensional equation. It might be a little more complicated than your original equation. It's not just a regular Markov process, it's a nonlinear Markov process, but it still has a huge dimension reduction, right? So it's beat this curse of dimensionality of trying to understand this very large. And so mean field limits are sort of used ubiquitously everywhere. Like, okay, you have any graph and you say, okay, now I'll do the mean field approximation and approximate. So let's see how well it works. So I just put some, numerical results for the discrete SIR process on the complete graph. And so the simulation is sort of blue, this is just the plot of the probability of being healthy versus time for some given initial condition, 0.8 probability of being healthy. And then, with some values, PQ that I chose. And then this is done by my undergraduate student, Mitchell Wartzman, who's now at University of Washington. But the plot of probability of being healthy versus time, you can see that you can't even see the difference, right? The mean field and the green. And this is not a very large graph. I think it was like 20 or maybe 30 nodes. So it does really well, right? On the complete graph as expected. But we have a limit theorem. We just don't know, we can also have quantitative limit theorems, and there's some really nice new results on those things as well. But now, how do they work on other graphs? If you look at the applied literature, you'll see mean field approximations are used on any graph because there's no other alternative. Like you have some other graph, you say, well, I'll assume that it's, very well connected, it's, dense, but how do you decide whether for a fixed n, whether the graph is dense enough or not, right? It's not obvious. So if you look at the numerical results for the SIR process on the cycle graph, and now you see that the mean field approximation. So each person has only 2 neighbors, right? And you're taking the number of, so cycle is n, so you're taking n to infinity. And then, well, the plot of the probability of being healthy versus time, it's clearly not doing too well. The blue is the simulation and the green is the mean field approximation. Okay, so it's not doing a good job.
Excuse me, just a quick question. Do we have a theoretical result on these cycle graphs?
I'm going to talk about that.
Okay, thank you.
Okay, thank you. So that's the motivation. Can we go beyond? So I wanted to show you that, okay, the existing approximations are not so good. Would anyone say, okay, you would expect it to be bad in the cycle graph. Might you do something else, given whatever you know? Anyone wants to conjecture? Like, why is it bad on the cycle graph?
Okay, I guess because on cycle graphs, the degrees remain the same for each node, no?
Yeah, so you don't have asymptotic independence. You know that you're strongly correlated with your neighbor throughout, right? So you do not have weakly interacting systems. You don't have asymptotic independence. And so the mean field limit is not doing well, right? So maybe, yeah, okay. So then the thing is, you might say, okay, maybe, yeah, it's clear the mean field limit is not doing well because you're not taking into account correlations between me and my neighbors. Yes, which we know exist. It doesn't go to 0 like it does in the other case. So what many physicists do or many engineers do is say, okay, so let me also write another equation for how the correlations evolve. And then let me, if that's not good, then let me write another equation for how, sort of 3-level interactions evolve and so on and so forth. And then, there's some ad hoc closure approximations that you take. These are called some refined mean field approximations, etc. But there's no real theory necessarily on how well these behave, and many of them still do badly. I have other pictures, which I don't have here, but I can show them to you tomorrow, that these refined mean field approximations still do quite badly on the cycle graph and many other graphs. Okay, so with that in mind, you want to go beyond mean field limits. And so here's our dynamics and here's our global empirical measure. And we want to focus in this class on what can we say about asymptotics for sparse graph sequences. So like I said, for example, if you have an Erdős-Renyi graph, G and Pn with NPn going to P in 0 infinity, this was an open question in Delattre, Giacomo and Dusson, say what happens in this case? Because they looked at the case NPn goes to infinity. Or you could look at a random regular graph, you know, with a fixed D. Okay, so, and many other. So I'm going to tell you what other kinds. So that's sort of the background. So the outline of the mini course is as follows. So remember that we have these 3 questions for this dynamics. You know, do the processes itself converge? And now I hope it's clearer what the difference between question 1 and question 3 is, because you can get a question 1 answer like Kurtz and Courtelinez without really getting sort of a Makin-Vlasov equation telling you what the dynamics is, as in question 3. And so the rest of this lecture, I will address question 1 and maybe if I had time, part of question 2. In the next lecture, I will address question 2 and establish some properties useful for question 3, and then get to the main point, which is question 3. Okay? Okay. And I would like to acknowledge all, so this is all work that we've done over the last 3 to 4 years. And this is, I'd like to acknowledge Dan Lacker and Ryobu Wu, who are former postdocs of mine who were very instrumental in a lot of this work, and my graduate student, Ankan Ganguly, whose work I'm not going to be talking as much about today because it talks about continuous time Markov processes, which are sort of the traditional interacting particle systems. And that has other complications that I'll have to save for another day. But okay. And then these are all undergraduate students who participated in various ways. So I'd like to acknowledge. Okay, so the rest of lecture 1, I'm going to introduce what's called the notion of local convergence, talk about the process convergence result that answers 1 and start on question 2. So of course, this is what we're looking at, either discrete time Markov chains or diffusions. And we want to ask if the process converges in a suitable sense. So it's obvious in the complete graph sense, or even the dense graph sense, you didn't have to ask much about GN. You just had to say that the number of vertices are going to infinity and then something loose on the degree in the case of dense graphs, right? You didn't have to worry about the structure of GN and how it's converging. But the point here is that we really want to understand when you have limiting dynamics that do depend on the topology of the graph, the geometric structure of the graph, then what happens, right? These mean field and dense limits says, you know, those are sort of topology independent limits. But, you know, you can have dynamics which you know that are going to depend on the topology, like in this first case. So now you can't just take an arbitrary GN and just say, okay, I just want the number of vertices to go to infinity. I can't take once a cycle, then a square, and then something else each time for each n, right? So obviously you have to have some consistency between. So if you look at static models, there's a very natural way of you might say if the GNs converge to G in a suitable sense, then maybe the dynamics XGN will converge to the associated dynamics in XG. You know, this is much in the spirit of Kurtz and Courtelinez, right? So there's some infinite dimensional SDE, which this converges to. Okay, and I'm writing a lot of it in the SDE formulation just because it's sort of easier, it's more concise, and sometimes the Markov chain versions are sort of, because they're discrete recursions, they're not as nice. Okay. So I want to remind people of sort of what is this notion of a graph GN converging to a limit graph G. So do most people are familiar with local convergence of graphs, or was this done in any other course? I'm just asking.
Not this year.
Okay, very good. So I'll do it.
So a bit of that in Luigi, but not formally.
Okay, I will do a quick review then, in the interest of keeping everybody aboard. So I also have an appendix. Sort of a write-up in terms of background that I will post. So if you are not familiar with this, you might want to read that before coming tomorrow, because we will use some properties of local convergence. And they're not very involved, so it should be easy to look at it just this evening or tomorrow. Okay, so a graph, we take a graph as a locally finite graph, which means, of course, all degrees are finite. And this could be an infinite graph here. And I have a special vertex, which I said, as I will note it, rho, and I'll call that a rooted graph. And I'll assume also that it's connected. And then I want to put some notion of closeness on rooted graphs. And we say that a sort of rooted graph converges locally to G if really for every finite neighborhood of the root, it becomes isomorphic. Okay, so this is saying explicitly that for every finite neighborhood, that is for every k, there's a large enough n such that there's an isomorphism of the graph from Gn to G such that these neighborhoods can be mapped to each other. Okay, so it's a very natural convergence notion. Okay, and so I think it's better to do it. This is why I decided to do slides today, and then I will write tomorrow. But okay, we want to see sort of examples of local weak convergence. So a cycle graph, near rho, when it becomes larger and larger, it looks more flat. Okay, and so it converges to a limit, right? So that's why many people belong to the flat Earth society, because they just look locally and they decide it's flat Earth. Okay, but okay, so then this only takes into account local convergence. On a line graph, obviously converges to the infinite line. A half line graph converges to the semi-infinite line. These are not at all surprising. And then a finite regular tree will converge to the infinite regular tree, right? So these are locally, so these are maybe the first example, which is not completely obvious, is in fact the d-regular graphs. So remember, the uniform random regular graph is just fix a d, and then among all d-regular graphs on n vertices, you select one uniformly at random, and then you place the root at a uniformly random vertex. And then it turns when at n goes to infinity, it still converges to a d-regular tree. And why this is not completely obvious is because you know that the tree, right, does not have any cycles, whereas the random d-regular graph could have cycles, right? So the point about this is it's saying that as n gets large, the cycles are getting larger and larger, right? So the probability of the smallest cycle is sort of going to 0. And that's really what McKay proved in 1981. Okay, so locally it looks tree-like, that you can take a large enough n such that there'll be no cycles of that length. Okay, so that's one. Then if you look at also the Erdős-Schwenny graph with npn going to a particular value p, then locally this random graph looks like a Galton-Watson tree with offspring distribution, Poisson offspring distribution, with parameter this p that it goes to. So what it's saying is that if you look at one of this, of course, here too, we know we have cycles, right? Like we have these cycles. But if you look for large enough n, since Pn is very low, so locally here, it will look like a random tree, a Galton-Watson tree, which means that you have independently, each vertex will have give rise to an offspring that are Poisson P distributed, and then each offspring again independently gives rise to further ones. It needs to go on. Okay, so it continues infinitely. Is that clear? Okay, so that's again another one that's not obvious, but maybe if you know local convergence, this is a sort of standard example. Then you can also show preferential attachment graphs converge to another kind of random tree. And there are many, the configuration model, for those who know what it is, converge to, again, a Galton-Watson tree with a different degree distribution, a configuration model with some moment conditions on the degree distribution, second moment conditions. So a lot of random graph models, which I'm not putting all of those because I don't, if you're not familiar with those models, it's fine. Just the Erdős-Schwenny is okay as an example. But there are many graph models that converge to random trees, okay, in the limit, as local limits. And if you're wondering, what do I mean by random graph converging? Remember that the local topologies I said can be metrizable. It's a Polish space. So it's just like any other random object. It's just converging weakly. Okay, whether it's taking values in the space of equivalence class of rooted graphs.
May I ask a question?
Yes.
So are there counterexamples that random graph doesn't converge to a tree?
Yes, I mean, of course, first you can just take a finite lattice, okay? That will not converge to a tree, that'll just converge to ZK, but you can also add some, to a lattice, you can add some random connections, it will not converge, right? So it's not like every random graph model will converge to a tree, where you can always make sure that you sort of ensure that you have a lot of cycles, then it won't converge to a tree. But sort of many naturally occurring random graphs do converge to a tree. Okay, to a random tree. Now, okay, we're interested in convergence of random graphs, but so we say, what are we trying to do? Remember, we're trying to show process level convergence. So we're trying to show that if Gn converges to Gn locally, then this process on Gn will converge to G, some process on G, right? The same process xg on G.
Can I ask one more question?
Please do.
So here we are taking the graphs rooted,
Yes.
but somehow the original model treated all graphs the same. So kind of, if we take a kind of a probabilistic local limit where we take random roots.
Yes. So I'm always choosing it here to be uniformly at random so that I get this notion of a typical vertex.
Oh, I see. So this is not a deterministic root. This is.
Yes, this is I'm choosing the root. So if you see here, like I just maybe didn't place the root at a uniformly random vertex.
Always. Okay.
Yeah.
And then the limit. Okay. So then the limiting thing could be a random graph, a random infinite graph.
Yes, it is. In fact, here, right, you have a Galton-Watson tree. If I choose here again, I should say here also I'm choosing it uniformly at random. So of course, if I choose it in a way that's biased towards something with higher degree, the root is more likely to be on a tree with a biased degree, you're not going to get a Galton-Watson, right? Because the root will have more higher degree than maybe some other typical vertex. But there are some cases also that even if you take, random roots in a certain other distribution, you may still get trees, but you have to be more careful. But here I'm always going to assume that we're choosing the root uniformly at random, because if you go back to our result, we want to understand what a typical vertex is doing, right? And so then it's natural not to bias any vertex because everything is homogeneous for the simplicity. Yes? Okay. Okay, so so now we said that we want to understand, we also have to understand, we also have initial conditions on these trees. So we can assume that these trees are marked. That means every vertex has a mark, where the mark is now just the initial condition, right, of that vertex. And then I'm going to ask that both the mark and the graph converge locally in the sense of marked graphs, which I'll tell you in a second. And then I want to ask if then the same graph marked with the whole trajectories that come from this dynamics, do they also converge locally? Okay, so let's first now at least it motivates why I want to mark these vertices, because what I'm interested is in dynamics. And so I need to first, of course, have some convergence of the initial conditions. And so a marked graph, again, you have some special root, and then you have marks on each graph, and the marks can be in some other Polish space. And then we say that this converges locally to Gx if for, again, every finite neighborhood and every epsilon, there's a large enough n such that I can find if an isomorphism that takes my BK finite neighborhood of Gn to the finite neighborhood of G in such a way that the marks are also close. So epsilon close with respect to whatever metric you put on your Polish space of marks. Okay, so this is just a very, very natural notion of marked convergence, local convergence, or marked graphs. And of course, whenever we're talking about this local convergence, we're only talking about isomorphs. So these G star will be the isomorphism classes of these rooted graphs. And when I say G star within brackets, it tells me where the marks are taking place. So this G star E will be, isomorphism classes of the marked graphs. Okay, and again, they admit a nice Polish topology, so we can talk about all random things in the usual way. Okay, so random elements of these. Okay. So let me now state the process convergence result. So remember, we want to look at this dynamics. And here, I'm assuming, remember, that F was continuous. And I'm also assuming that these are IID with the same law for all graphs. Okay. And then I'm assuming here that, so by the way, for this result, you don't really need this homogeneity. But since for the final result I'm looking at, I would just rather stick to all homogeneity. But Omar, just to ask you, answer your question, I can have these V's depending on V and sigma depending on V for this one. Okay, and then where the B and sigma here are Lipschitz continuous, so sigma as well. And now let P, Gn, Xn then be the law of this, Gn, Xn, which will be taking values in these marked graphs, equivalent